Hello, welcome to Hawk Math. Today we're going to be doing the integral from 0 to 1 of the floor of the log base a of x dx. Now, when I first see this problem, I immediately want to get rid of this log base a of x because it's really messy and I don't know how to take the floor of it. So to do that, I'm going to use simply u sub. U equals log base a of x, and so that makes a to the u equal to x. Now, finding du, we have a to the u ln a du equals dx. Plugging what we have back in, we get the integral. Okay, the lower bound, plugging in 0, this is going to go to negative infinity. So you have negative infinity. And then upper bound, plugging in 1, we get 0. Now we have the floor of log base a of x is u. And now dx is a to the u ln a du. Now, how do we proceed from here? It's not very nice because we have this floor. Well, whenever I see the floor function, I like to actually split this up using a summation. Now this takes a little bit of creative sight to see, but once you practice it, it'll become more natural. So in order to do this, I'm going to set this equal to the sum from n equals 0 to infinity of the integral from negative n minus 1 to negative n of, and we'll get to that in a second, but look what happens when you do this. When you plug in n equals 0, you have the integral from negative 1 to 0. And then you have plus the integral from when n equals 1, which will be from negative 2 to negative 1. And then you have plus the integral when n equals 2 from negative 3 to negative 2. And if you add up all of those integrals, then you will get this in the original integral. So what goes inside here? We have the floor of u, but notice on one of these intervals, the floor of u is always going to be equal to negative n minus 1. So we have negative n minus 1 times a to the u ln a du. And that's why it's nice to break it up in the summation whenever you have a floor function, because now this floor function is just a constant that we can ignore in the integration. So now what we need to do is integrate this with respect to u. And that's pretty simple because we have the sum from n equals 0 to infinity. Okay, now integrating this, which is going to bring us right back to a to the u. So we have negative n minus 1, bringing that to the front, times a to the u, evaluated from the bounds, negative n minus 1 to negative n. And there we go, our integral is completely gone. We dealt with the floor. So plugging in our bounds, we have the sum from n equals 0 to infinity of negative, I'm going to factor out the negative, so you have negative n plus 1 times a to the negative n minus a to the negative n minus 1. Now how do we proceed? Well, I want to change the index so we can get rid of this n plus 1. So I'm going to just set I equal to n plus 1 and then re-index this. So you have the sum from I starting at 1 now and going to infinity of, well, we'll just have the negative I, but I'm actually going to bring this negative sign into here. So we'll have a I times the quantity. Now, what does this exponent become? Well, so we want to solve for negative n minus 1 in order that we should negate this. So, remember, negating this and flipping this, we have a to the negative I. And this part right here, what is negative n? Well, we see that I minus 1 equals n, so negative n equals 1 minus I. So, now we can plug that into here, so you have minus a to the power 1 minus I. Now, all we need to do is finish this off. So, I'm going to rewrite this, actually, in terms of fractions, so it's easier to tell what's going on. So we have the sum from I equals 1 to infinity of I over a to I, and then we have minus I over a to the I minus 1. Okay, now when I look at this, I think it's going to telescope, because we see we have this cascading I and I minus 1, so the terms might cancel out in some neat fashion. So I'm going to start writing out the terms and see what happens. So we have, plugging in 1, we have 1 over a to the 1, minus, plugging in 1 over here, we have 1 over a to the 0. Okay, now plugging in 2, we have plus 2 over a squared, minus 2 over a to the first. And then plugging in 3, we have plus 3 over a cubed, minus 3 over a squared, and so on. Now let's look at what cancels out. So we have this a to the 0 in front. So you have negative 1 over a to the 0. Now we have these a to the 1s. And notice this 1 minus 2 will go to minus 1. So we have minus 1 over a to the first. Now looking at the a squared from the denominator, we have a plus 2 and a minus 3. So it's going to be another minus 1 over a squared. And if you notice, that pattern will continue. So we'll have that going on forever. So now what we need to do is solve a simple geometric series. Okay, so I've cleared up the board. We each take the first term, which is negative 1, over 1 minus the ratio. The common in the ratio is 1 over a. So all we need to do is simplify the fraction, so I'm going to multiply by a over a. So negative a over a minus 1, and then bring the negative sign to the denominator, we get a over 1 minus a. And that is the answer to this in terms of a. So this integral is not actually that bad once we employed this substitution to get rid of the log, and then we also cleverly got rid of the floor function using a summation. So this is a very common trick that I use a lot. I hope you enjoyed this video. Please like and subscribe if you want to see more like it, and free feel to leave any comments or suggestions down below.